right, good morning. Hope you all are doing well. So last time we looked at structures, and so we saw that the basic idea with the structure was that you could store many different values together, but it was also different from an array in that you were able to store values of different types. So whereas with an array, we always have to commit to one type, such as an array of integers or array of characters or maybe array of strings. We saw with the structure that you could have different fields or variables, but they could also be of different types. And so we were looking at an example with that student structure, and we had four different fields within it. So one was a name of type string. We had an ID number that was an integer type, and we had a character for the letter grade, and then double for test score. So four different fields of four different types. And then we looked at several examples as far as the basics of using structures. And so we saw that just like when you're dealing with an array, we have to think about the issue of accessing individual fields within the structure. But whereas with an array, we work off of index numbers, with a structure, we give each field a specific name, and then we reference that field by name whenever we want to access it for that particular object. So if we had created a student object and then we wanted to set the name field, you could take the name of the object, and if we called it Stu or Stu2, for example, and then we could use that dot operator with the name of the field coming after the dot. So that was the basic syntax that we saw. It was the name of the object on the left of the dot, and then on the right-hand side of the dot would be the name of the field. So the dot operator itself was really used to select or choose which member of the structure that we want to access in the given moment. And we saw how to combine structures with things that we're already familiar with. So we saw that in general, we can do things like combine structures with arrays, or combine structures with functions, either as by having it as a function parameter or as a return value. We also saw that you can combine it with pointers. So essentially, right, all the things that we can do with primitive types, we can certainly do those kinds of things with structure objects as well. And we saw, for example, when you create the structure object, you can either create it uninitialized, or you can do things like full initialization or partial initialization. And another thing that we looked at, which we're going to see a whole lot of now that we transition into linked lists, is that arrow operator. So we saw some examples of that when we looked at that code project for the structure project. And we saw how that arrow operator was being used as an alternative way to deal with things like dereferencing the pointer. Because we know, certainly from our discussions back in chapter 9, that the name of an array can be treated like a pointer, or we might have things like a separate pointer that we're working off of. But what we saw in terms of syntax was that you could have the name of the pointer on the left-hand side of the arrow, and then on the right-hand side would be the name of the field. So things like PTR, arrow name, or PTR, for example, arrow ID number. And the idea was that the arrow operator was really doing two things for us. It was dereferencing that pointer and then applying the dot operator to access that field. So a statement like the PTR arrow name, we saw last time that was really equivalent to star PTR, right, dot name, where we had to also have those parentheses to force the dereferencing to be applied before the dot operation. But that's what the arrow operator was doing for us, is it was really doing In one operator, it was doing both of those things, both the dereferencing with the star and then the applying of the dot operator as far as accessing the correct field within it. And so now that we have the idea of making structure objects and using those structure objects, now we can look at linked lists, where we're going to be creating a list of objects, but the way that they're connected together is through pointers. So we've looked at things like an array of objects, and that was also part of your assignment, where meaning that all the objects are going to be stored contiguously or back to back in memory. But with a linked list type of setup, we still think of them all as being connected together, right? That's why we call it a linked list. But the difference comes down to the memory situation. So we know with an array, certainly any type of array, whether it's an array of primitive types or an array of, for example, structure objects, we know that the elements of the array are stored together as a group, but with the linked list, the nodes, or meaning the objects, are not stored together. But we will still be able to do things like start at, for example, the beginning of the list and work our way towards the end of the list, right? So similar to how you might do that with an array. So meaning we can have a loop like that, but the idea is that the nodes or the objects are not stored together in memory, but they are going to be connected to each other through pointers. So everything comes down to following the pointers to work our way from one end of the list to the other. And there's certain advantages, right? So for certain types of operations, right, linked lists can be, better performance than arrays. So we know that certainly one of the big benefits of arrays is the fact that you can directly access any element in the array without having to access any of the others. And we know that that works because of the fact that they're all stored together back to back. With a linked list, right, we're not in general going to be able to do that. Because we could have, a small list, we could have a very large list, and it's not going to really be practical to have a separate pointer to every single node. So typically what we do is we definitely will maintain a special pointer to the first node or the beginning node, which we sometimes call head. And in some cases, we might also choose to maintain a pointer to the last node, especially if we're doing what's called a doubly linked list. With a single linked list, we may choose to not do that. But in general, right, you're going to always be starting at one end of the list, and then you're going to have to work your way to get somewhere else. Whereas with an array, because of random access, we can go anywhere immediately without having to go to the previous locations first. But when you think about things like an insertion type algorithm, for example, taking a linked list in a current state and inserting a new node somewhere within that list, well, we know with things like an array or a vector, which is just a dynamic array, we talked about those kind of issues a little bit back in chapter 7 when we looked at things like the vector class and the fact that it has functions like push back and pop back, but it doesn't have a built-in, for example, push front or pop front, although we looked at how you could still implement that function. But one of the things we mentioned was that really adding to the front of the structure especially was not really the most ideal situation for a vector, because you have this whole issue of having to shift the other elements around to make room for the new element that you would be putting at the front, right? Because you can imagine if we have a vector dynamically created of a certain size, and then we want to insert a new element now at the beginning, well, we're going to have to move all the old elements down. Now, whether we have to dynamically reallocate the vector somewhere else depends on whether the new element is going to make the size, right, for example, exceed the capacity. But either way, we're at least going to have to shift, all the elements around to make room for the new element that's now going to be at index 0. Whereas with the linked list, as we'll see, we don't have to do that, right? We don't have to shift things around to make room for a new element, since everything revolves around pointers, and since the nodes are not stored together in memory. So it's a different way of managing things and thinking about the structure of the data. Or even inserting, if you think about things like inserting in the middle, that's not as much shifting for an array compared to inserting in the front, right? Because, you know, if you insert in the middle, then there's some elements in the array that would have to be shifted and others that don't. But similar idea with the linked list, still there's no shifting that has to take place because of the way that it works. So there's, you know, just like anything else, you know, there's always trade-offs. Nothing's, you know, usually the best all the time. But there are those situations where, you know, linked list does have advantage, and there's certainly times where, in situations where an array type of setup has an advantage. But that's the idea. So linked lists really are a combination of the object, which for now we're working off of structures, and pointers, because pointers are how the different objects are going to be connected to each other. So we're going to be creating what are originally a bunch of, in effect, separate nodes or separate objects, but the way that we're grouping them together into a list is through pointers. And so what we can do is, as a starting point, is in the structure declaration, we had things like string for the name, integer for the ID number field, letter grade of type char, test score of type double. So those were the data values, right? Those were the 4 data values that we wanted every student object or student node. We use the term node sometimes with linked lists, but a node just really is referring to the object, right? In this case, the structure object. But those are the 4 data fields that we needed to store in each object. But now we're going to be adding at least one more field. And we'll first look at what's called a single linked list, where the links only go in one direction. But the extra field is going to be a pointer type. And the idea is that this extra field is going to be able to point at an entire student structure object. And by putting it in the structure declaration, it means that every student object is going to also have this pointer, this new pointer field. And that pointer is going to be pointing at either another student object, or it's going to be pointing at null PTR if it's, for example, the last of the nodes in the, or last of the objects in the linked list that we're forming. And we'll see that that's, in general, a common way of also checking for when you've reached the end of the linked list that you're forming. But that's the general idea. So we still think of it, you know, at least conceptually, as one type of structure, which we call a list or a linked list. And in that sense, we think of the nodes as being linked or connected to each other, but it's also important to keep in mind that they're not stored together in memory. So this is definitely, you know, a different approach compared to the array approach, where everything is always stored together. And again, we've been hinting that there's certain advantages, like the idea of inserting like things like a new node, for example, at the beginning of an existing linked list, or even somewhere maybe in the middle, because whereas with an array, you would have to shift elements around to make room for the new element. With a linked list, we don't have to do that because of the way that it works. And because we have more flexibility with the linked list, given the fact that the elements are not stored together in memory. So whereas with something like a vector, we know that, for example, part of the overhead that's involved is when the size reaches the capacity, since it has to be the case that all the elements are back-to-back in memory, we have to find a whole new block in memory that can accommodate the new larger size, right? Redynamically allocate the vector in that now larger block, and then do things like copy the old elements over to new vector. But with the linked list, since we're not, having to always declare them together as a group, we have more flexibility in terms of where they're at in memory, because we could have one node over here in memory, one node over here in memory, right? They can be all over the place in memory, but they're still connected through pointers. So we have more flexibility in that sense, right? In terms of where the nodes are actually physically located in memory, since we don't have to store them as one big block as we do with an array. So that's, on a conceptual level, that's the idea of what we mean by a linked list. And we'll first look at what's called a single linked list, which means that we're going to have the links go in one direction. We'll eventually look at the idea of what's called a doubly linked list, where the links will go in both directions. But the idea with the single linked list is we'll maintain a pointer called head to the first node, or we'll see that if the list is empty, then head will be pointing at null PTR. And the idea is you can always use head, right, as your kind of your starting point or your entry point in the list. So start with the head node, and then following these pointers that each node is going to have, which we'll see that pointer, meaning the pointer that's actually in the structure declaration, is usually called next by convention. And that pointer will take you to the next node within your linked list. So that's how we can, for example, do things like start at the beginning of the linked list and then work our way towards the end of the list to the last node. We can do that by following those next pointers to go one by one from the head node all the way down to the tail node, which is the last node in the list. And we'll also look at dynamic memory allocation here as well. So dynamic memory allocation in general is something that's very common with building a linked list, because it also allows us to create really any number of nodes without having to give those nodes a name. Because again, it's not an array. So with an array, it kind of works itself out, right? Because either you create a non-dynamic array and then you give that array a name like A or R, or you create a dynamic array, but then you have your pointer, right, that points at the beginning of it. But with a linked list, we're not just creating one entity, right? Because it's not just one big array, it's actually a bunch of different nodes. But in general, right, we don't want to have to give every single node, for example, a different variable name. So we can just use the new operator to dynamically create nodes as we're going along. And then just like we saw back in last time and also back in chapter 9, we know that when operator new is used, the thing that we're allocating dynamically is not given a name, but it is being linked up with a pointer, which will ultimately be used to access it. So we'll be able to do things like dynamically create however many nodes or objects that we need to have on our list, and then manage everything through pointers. So in that sense, we don't have to go through the whole process of coming up with all these different variable names for every node in the list. Because the whole idea is that we're not going to be maintaining, right, a specific pointer to every single node on the list. We're going to be doing things like maintaining a pointer to the first node, and then everything is going to start relative to there. Or eventually, as we'll see, if it's a doubly linked list, then we'll have a pointer to the first node and the last node, and we'll be able to iterate throughout the list in either direction in that case. Okay, so we'll start with our modified structure here, and then we'll look at the case. For now, we'll just look at a case of, as a starting point, is building what you might call a hard-coded list. So there's going to be in the beginning a couple of nodes, and we'll see the basic idea in terms of how we can set them up through connecting them together through the pointers. But in terms of the structure, the actual structure declaration, for now at least, the only difference is we're going to have the same 4 fields that we had before with the structure project that we looked at last week. But in addition to that, we're going to have that new field called next, which is a pointer that is capable of pointing at a student structure object. So this will be the entire basis as far as how we're going to physically connect all of these different linked list nodes together, is through this field called next, which is going to be in the structure declaration itself.